we're going to talk about the model put forward by Niels Bohr of the hydrogen atom based on what we've just discussed, right? So we talked about quantization. Well, we talked about the fact that the energy of an atom of a heated solid, according to Planck, its energy will be changed by integral numbers of a quantum of energy. And it was Einstein who suggested that the energy that is emitted or absorbed by a heated body exists as packets known as photons. So we're going to tie all of those things together in discussing the Bohr model of the hydrogen atom. So Bohr, based on what was discussed before, he found out that the electron energy is quantized within an atom. In other words, the energy of an electron can only have specified values. So each specified value is called the energy level of the atom. And based on that idea, he came up with this model, right? The model he came up with is an atom where you have the nucleus at the middle, and then the electrons will be traveling in well-defined orbits surrounding the nucleus. In some textbooks, they call this the planetary model. So basically, based on this model, he came up with this equation. The energy of an electron in a particular orbit is equal to minus RH divided by n squared, where RH is this constant here, 2.179 times 10 to the minus 18 joules, and n is an integer which designates the particular orbit. So for the first orbit, n is equal to 1. For the second orbit, n is equal to 2, and so on and so forth, right? And what you'll find is that as you go away from the nucleus, from one orbit to the other, the energy of the orbit will increase, right? So as n increases, and because of this negative sign, the actual value of the energy will increase as a result. So the energy increases as the orbit is further away from the nucleus. One important thing I want to mention here is that the negative sign represents the fact that you have a force of attraction that exists between the electrons in the orbit and the positively charged nucleus. And speaking of the nucleus, we have to take into account the charge of the nucleus as well. Now, let me just say that the Bohr model works for hydrogen, but it also works for any one electron structure, right? And the reason why I mentioned that is because hydrogen is not the only one electron structure. You can have other one electron structures that can exist, and we can use the same idea and use the same equation. Now, if you're dealing with anything other than hydrogen, you have to take into account the charge on the nucleus. So we have to modify this formula here, and it becomes this formula. The electron energy of a particular orbit is equal to minus RH times z squared divided by n squared, where z is the charge on the nucleus of that particular structure. So for example, and let me go here and erase. Oh, I can't erase this. Okay. Please ignore what I have here. In fact, what I'm going to do here is draw some lines through this so as to avoid any distraction as far as this is concerned. Let's say we're dealing with the helium plus charge ion, right? Now, this helium ion will have a charge on the nucleus of +2, but it has only one electron, right? So we can use this formula, En, for the electron. The energy of the electron will be equal to minus RH times z squared, which in this case would be 2 squared divided by n squared, all right, which simplifies to minus RH times 4 divided by n squared, right? So basically, we can calculate the electron energy depending, of course, on the orbit that the electron is in, using this formula for the helium ion, right? So the point I'm getting at is that this particular equation works not only for hydrogen, but for pretty much any electronic structure which has only one electron in it. Okay. Also, I want to make the point here, which is stated here, is that if the electron is located infinitely far away from the nucleus, then the energy would be 0, which makes sense based on this equation right here. If n is equal to 0, then the energy, or if n is equal to infinity, I should say, then the energy of the electron would be equal to 0. Okay, so based on that equation, then we can use the Bohr model to explain the line spectra that we discussed earlier, right? So basically, according to the Bohr model, whenever you have an electron making a transition from one orbit to the other, then there'll be a corresponding emission or absorption of energy, which would be equal to the energy differences between the two energy levels, right? So the energy difference will be given by delta E, right? And if we look at the equations for different energy levels represented by these two expressions right here. So EF represents the final energy orbit. That will be equal to minus RH over NF squared. And EI, which is representing the initial energy orbit, that will be equal to minus RH over Ni squared. So the difference between these two would be the final minus the initial. And we put these terms here. So delta E, let me put this first. Maybe I should have written this somewhere here. Delta E will be equal to E final minus E initial, right? So if delta E is equal to this, then this term here would be for E final, this term here would be for E initial, and then when you simplify it, you're going to get this expression right here for delta E. So delta E would be equal to the minus RH times 1 over NF squared minus 1 over Ni squared. And that gives you the value of the energy of the transition that is taking place, right? Now, let me just mention here, I'm going to write it over here. If N final is greater than N initial, right? In other words, I'm sorry, if N final is greater than N initial, based on this equation here, that means that delta E is going to be positive, right? So if this value here is greater than this value here, then delta E is going to be positive. On the other hand, if N final is less than N initial, then delta E would be less than 0. Now, if delta E is positive, that means that energy is absorbed in the form of radiation. So energy is absorbed. However, if delta E is negative, that means that energy is emitted. All right? And the energy will be emitted in the form of radiation, and in some cases, as in the case of hydrogen, in the form of radiation representing light of a particular color. All right? So that's basically how the Bohr model is used to explain the line spectrum of hydrogen. So what you're looking at here is basically all the possible forms of radiation that is emitted in the case of the hydrogen atom. All right. Now, some of these represents the different colors of light that we can observe, right? Which we saw a couple of slides earlier when it comes to the line spectrum of hydrogen, right? But there are others that we simply cannot see because these forms of radiation falls outside of the visible range. So collectively, these are called the Lyman series, and these over here are called the Paschen series. We cannot see them, but they can be detected using particular instruments. But the Balmer series are the ones that we can actually observe and measure, all right? With our eyes, that is. So that's basically how the Bohr model is used to explain the line spectrum of hydrogen. Okay, we're going to stop here, and then we're going to go further into a discussion of the line spectrum and further explanations concerning the electron transitions, how they explain the line spectrum for different elements. All right, until next time.